So hello everyone, my name is Betül Durak from cryptography team. Today we have Olga Sanina from Technical University of Darmstadt, and she's joining us from Germany, remotely unfortunately. She's going to talk about the Bluetooth protocol stack and most importantly the security and vulnerabilities of that stack. And stage is yours, Olga. Welcome.
Thank you for the introduction. Thank you also for inviting me. It's really nice to have so many people interested in Bluetooth and really looking forward to my talk. So before I start, I will give some disclaimers. First of all, I'm really passionate of Bluetooth, so I really love it with my heart. And sometimes I can say things like I like or I dislike. So in this regard, all the opinions are on my own, not of my employer or of my co-authors. It's only mine. Then I will also show you some attacks. And these attacks are publicly known. They have been disclosed, but just to be sure that I'm not going to show you anything like what is not publicly known so far. And finally, as I show you some attacks, they're only for the educational purposes. Like it's not a guide how to hack Bluetooth or anything. I do not encourage you to do so. So just enjoy the talk. So Bluetooth is almost like everywhere, right? We use it, I don't know, for example, now I have the headphones and they're connected via Bluetooth. So when we talk about Bluetooth, we talk about two types usually. First one is classical version or basic rate enhanced data rate. So I will probably use both these terms, so you might need to remember this. And this type of the connections in Bluetooth is more stable. So you might need it when you want to stream some data. Like, for example, with the headphones, you still want to hear the people talking about, or in the car, for example, or if you play some video games, you also want to have really good connections. And there is also the low energy version that was used mostly for devices that do not have really high memory or they do not have high energy. So they have like small battery. And these are usually like smartwatches or, I don't know, lockers and some controllers. There are also some devices that can use both modes, so-called dual mode. And these are usually our smartphones or our laptops. And there is something also interesting as Bluetooth mesh. So this is mostly used for mesh networks, so that each devices can talk to each other and not through some central one. In this talk, I will not talk about Bluetooth mesh. It's just for you to know that, okay, it exists. I will focus mostly on classical version. Maybe a little bit I will touch low energy, but let's see. So now you might ask me here, okay, where is contact tracing here? Because this is what people usually ask me. So contact tracing is a little bit different kind of. So it still uses Bluetooth, but what I'm going to talk today is about connections that are long-term and they use bidirectional communication. While contact tracing is usually just beaconing. So you just send some message and then you forget about it. Like you do not get any response. And these are not long-term relationship. It's just like you're just sending things and that's it. All right. So when we want to connect Bluetooth devices, I guess some of you might know, then we basically take these devices and then we need to discover them first. So if you ever connect it, they first need to go through some pairing process. And this pairing might be like you see some digits displayed on your screen, or maybe you do not see anything, but you still see that the devices are pairing. So, and the same one you will see, of course, on the other device. And when you did this initial pairing and the devices kind of remembered each other, then you can also just connect anytime because you already know this device and it's saved. So for example, I'm using headphones right now. So whenever I just want to use them, I just open the saved devices. I click the button, okay, this is the device that I want to connect with, and then they're just connecting. So this is how it looks from the user perspectives, but let's look how it looks from a little bit more crypto perspective. So it's still a very high level protocol description. So we again have this initial connection and we have reconnection, and it starts with the physical connection on the physical layer level. So this is because we use wireless communication, right? So we still need to exchange some physical information, like what frequency we're gonna use, what channel we're gonna hop, and so on. Most importantly for us, here we send over the device address. You can think about it as the MAC address of the devices. So there is also mechanisms to change this one, but you can only just think, okay, this is the MAC address. Then the devices need to connect on the logical level. So they exchange what are their capabilities. Like, can you do this or that protocol? Can you use these algorithms? What size of the key do you support? Like such information that helps to make a decision on what exactly protocol out of the protocol stack you will be using. And then the pairing happens. So here I have it for the secure connections, which is the most secure protocol in the stack. And it consists of the elliptic curve Diffie-Hellman key exchange. When the devices just exchange some public shares, then they exchange the nonce, and they do some kind of key confirmation on what they exchanged before. As a result of this communication, they derive the so-called Laine key in the Bluetooth Classic or long-term key in Bluetooth Low Energy. So what enters the computation of this key is the key that we exchange, so that we derived during the elliptic curve Diffie-Hellman, then also the nonces that we exchange, and the device addresses from the physical level. For Bluetooth Low Energy, this is ISC-MAC computation, and for Laine key, this is HMAC computation. So now when we have this key, we can just use it anytime to reconnect again. So what do we do? Again, if we were not connected before, then we need to, again, establish a connection on the physical layer, exchange our device addresses and so on. And then we can go exactly to the session key establishment. And this is to derive the encryption key. So not the long-term key or the Laine key will be used for encryption of the data, because it will be just stored, but the encryption key. And this is the key that you will be using for one session. And whenever you disconnect, then you will derive a new one. So what enters the computation here is the long-term key or the Laine key, and the challenges that were derived, that were exchanged during the session key establishment. Okay, I hope I'm not going too fast. I'm not sure how people are familiar, but in case you have some questions about like high-level protocol description, you can just shoot me with questions.
Can I ask some questions?
Sure,
just
sure.
to clarify, make sure. So when you do this initial connection, so basically this key confirmation, so this link key is. So this is a long-term key. Basically, when I store that device, say I connect my laptop to my headphones, basically I store this link key, and if I erase the device from my list of Bluetooth devices, then the link key is gone. Exactly. Is there ever any reason to refresh this link key otherwise, or is it just it's going to remain there for as long as I have the device stored?
So you might want to refresh it if it was compromised. So if you know that maybe there was an adversary, or you know that it was leaked somehow, that it's got access to your device. Sometimes it also happens that you might run into the error and your device is just not reconnecting. So you try, but they do not establish the connections. Then you need to forget the device again and pair from the scratch. But apart from that, no.
Okay, and in terms of the logical level and these capabilities, basically, I mean, I don't know if you know this, but so, like, what if I create my own Bluetooth device that does something that's never been done before, right? So this, I don't know, it releases some food for my cat, and I mean, obviously, I guess. Obviously, like say the Windows Bluetooth driver isn't familiar with this kind of capability, right? So can I like somehow how can I just tell my Windows device, for example, that you can somehow pair with this Bluetooth device that has this kind of capability? Or
okay, I see the question. So in the core specification, they define only several capabilities that you can have, such as you have only display, you have only keyboard, you have display and keyboard, you have no display, no keyboard. What else did I miss? Okay, so they have like specified entries here, but they also have some strings reserved for the future use. So for example, if you send me, I don't know, beat string with, I don't know, digits, well, let's say number 10, then I don't know what is that, and I'm gonna just reject. But it can be that on the application layer, for example, some manufacturer introduces something new. For example, I can have, I don't know, the hearing opportunity, right? Because I can hear maybe the passkey through my headphones. So this way you can say, I use this research for the future use with the bit 10, and then I send it over. And if the device also supports, or if it's from the same manufacturer, then it will recognize what it is. But it's not specified in the core specification. So it might be specified by something else. Like, I don't know, specifications of the phones, smartphones, like anything of the device, but not in the core specification. But yeah, you can modify this, and I guess some devices might do this, but I'm speculating here.
Okay.
But
okay.
yeah, it's definitely possible.
Okay, it seems we have more questions. Aisha?
Yeah. So the first thing is in the secure connection case that you showed. I know it's a very high-level protocol, but are there multiple different protocols to establish this secure channel? Like,
there are actually. So there are legacy protocols which just used, I'm talking about Bluetooth Classic now, which just used PIN. And this one was not secure even against passive addresses. So it was possible to just brute force. Then as a solution to this came the SecureSimple Pairing protocol. So this one also has 4 variations depending on the input and output capabilities, like numeric comparison, passkey entry, out-of-band communication, and just works. And then there is also secure connections, which is based on the SecureSimple Pairing, but just they use the bigger elliptic curve for this one. Kind of similar thing is happening in Bluetooth Low Energy, but they did not a nice thing with the naming, because they said that we have SecureSimple Pairing, but it's not secure even against passive adversaries. That's the problem. But the idea is also kind of the same. And the reason why it's not secure against the passive adversaries is because there is no elliptic curve involved. No elliptic curve Diffie-Hellman or any kind of Diffie-Hellman. And then they have also secure connections, and this is exactly the copy of the secure connections in Bluetooth Classic. So here I show exactly the secure connections for Bluetooth Low Energy or for Bluetooth Classic. But yeah, there are like a huge variety of the protocols that you might use for pairing.
I see. And this is not just the crypto level, I guess the key confirmation also changes, whether it's passkey or PIN. Is that true? Or
exactly, like everything changes there. For example, in legacy, it will be completely different. So key confirmation would stay the same for SecureSimple Pairing and secure connections, but the nonce exchange will look a little bit different. So in some cases, they will first commit and then reveal the nonces. In some cases, only one party will commit and reveal the nonces, such things.
I see. And
so
the key
they look a bit
confirmation. So to say the key confirmation always is manual, in the sense you would expect the human user to input something, or
actually it happens a little bit before. So during the nonce exchange, the devices first commit the nonce and then they reveal it. And then based on this, they might compute some digits and then display to the user, and then the user checks and confirms it here. And then they will run key confirmation on top. So you can think about key confirmation as they use the MAC key that is derived from the elliptic curve Diffie-Hellman key exchange. Then they include all the transcript that they had, like what nonsense we exchange, what input-output capabilities we exchange, what device addresses we exchange. They took this whole bunch and they just compute the MAC and they send over. So this is what the key confirmation is.
Thanks.
Sure.
So I have a question. So I'm more of a systems guy, not a security person, but to run ECDH, I think each other uses their public keys, right? Is that
exactly.
Is there a step where they verify the public key? For example, say when my laptop says this is the laptop's public key, do they usually go through a kind of a certificate chain kind of thing to validate the public key, or how is that done?
So unfortunately, they do not do this check, but it would be really nice if they did. So what they just exchange here, so they generate a pair of the secret and public key, then the public key gets exchanged. Sometimes it's generated each time, but the specification also allows to reuse it in up to 8 connections, if I'm not mistaken. There is validation, but it's not like the public key validation. It's more like, okay, are we on the same curve? Do we still use like the valid curve? Or did you use some, I don't know, you put Y coordinate to 0, like such things. Or maybe you send my own key. So they do some kind of small checks to prevent some of the attacks, but they do not validate that it's really coming from this device or that device.
Okay, yeah, that's what.
I see one more question from Paul.
Is an opportunity for certificate exchange defined in this setup protocol?
Yeah, actually going ahead because this is what we did. So in this term, no. In this initial connection or reconnection, no. But you should be able to build it on top. Maybe not with these keys. Maybe you need to generate a new pair of keys also with the certified authority. But here, yeah, it's not possible here, unfortunately. Yeah. Okay. I don't see questions anymore. All right. So I'm not sure what exactly happened, but at some point there were really many attacks on Bluetooth. And they were really different. So for example, one of the attacks was on the logical level, where the parties negotiated what size of the key they want to use. And it was possible to downgrade the key size up to 1 or 7 bytes, which is really horrible. Then there were also attacks to downgrade what the protocol we want to use. And this is the case because we do not authenticate this choice. We just exchange, okay, this is what I can do, this is what I would like to do, and that's it. So even though we confirm it later, there is no proper authentication in the cryptographic sense. Then there were also some attacks on one of the protocols, or more protocols in the stack. And this is exactly the problem in case we have some attacks like method confusion attack, where we exploit 2 protocols and we intertwine with them. Then, of course, there were also attacks on legacy, which I mentioned, when it was just possible to brute force the key. There were also some attacks on the session key establishment mechanism, but it was mostly on legacy key establishment or on the Y wings of the protocol. There is also something that I didn't mention so far, but there is also a possibility to derive the key on a different type of Bluetooth or on different transport. So for example, if we connected with some device on a Bluetooth Classic type, it was possible to switch or to derive a new key for Bluetooth Low Energy. So this is what is called cross-transfer key derivation, but this mechanism was also found not to be secure. It was possible to replace the keys or to derive the keys that are not really secure, and so on. I will show some of the attacks. I think I still have some time. So I will show like my favorite attacks on Bluetooth. So there was a blue mirror attack. What is happening is we have 2 devices. They commit the nonces and then they reveal it. But if we have the adversary who just pretends to be the other device, and this adversary just mirrors whatever it received, then it was possible to do the authentication. So these kinds of checks should be done. But as you can see, like this attack was discovered in 2021. So there is still a huge field of attacks in Bluetooth. Another attack that I really like is the method confusion attack. So there we again have 2 devices. And during the logical level connection, they negotiate what exactly they can do. But for example, one says, okay, I can compare the digits or I can also enter them. And the other device also answers, okay, I can also do both. But if we have the adversary in between, then the adversary can modify this value and say, oh, actually, I cannot do compare or enter. I can do only one. And the same happens with the other connection. So now what happens, the devices will enter different protocols. So on the right side, it will be the numeric comparison. And on the left side, it will be passkey entry. So what does it mean from the cryptographic perspective? It means that both connections will have different keys, and the adversary will be sharing these keys with the victims. But from the user perspective, and we have the user who just, okay, I see the digits, and I just confirm them or I enter them, it looks legit. So from the user perspective, it looks like, okay, the genuine connection because I confirmed something or entered something. But from the crypto perspective, it was two completely different protocols. It was completely different nodes and hence completely different keys were derived during this connection. Okay, questions here?
Yes. So what exactly do you mean by compare digits? So is it like you'll enter something like yes, or like what exactly does it mean? Is compare
So
digits
usually,
versus enter?
Yeah, this numeric comparison, you have two devices and both display the digit. You as the user, you need to compare if they're the same, and then you press the button if they're the same.
Okay. Yeah,
so it will be yes or no button.
Thanks.
And for enter, it would be one device is displaying some digits and you enter it on the other device. Or it can also happen that you just come up with the digits yourself and you enter them on both devices.
Thanks.
Yeah, sure. All right. So another attack that I really, really like is on passkey entry. So when we show the digits on one phone and or one device and enter the digits on the other one. So we have the user who wants to connect a keyboard with their screen. Okay, looks good. So what happens is some digits are displayed on the screen. I hope it's not 1, 2, 3, 4, 5, 6 because it's kind of easy. And then the user needs to input the same digits on the keyboard. But what is happening at the same time is the attack. So the adversary connects its fake screen to the keyboard, for example, using some not secure communication protocol, like, I don't know, JustWorks or legacy protocols, or maybe the adversary had like physical access to the device. But now whatever the user inputs on this keyboard, the adversary will see on the screen. So this way, the adversary can learn exactly the passkey that was used by the user and use this passkey to connect its own fake keyboard to the screen. And here we will have exactly proper connection, like proper in the sense like authentication in Bluetooth. So here we will have what Bluetooth core specification calls authenticated connection. But the thing is that in both these connections, the adversary will compute their own link key or long-term key with the user. And from the user perspective, it again looks like, okay, nothing happens because I compared the digits or I entered them. So it looks really legit. Okay. Other questions on this attack? All right. So these attacks that I presented and some more, they are publicly known and they're reported on the website of Bluetooth Special Interest Group. What they also do there, they release a security notice. So they tell what the manufacturers or the developers of maybe Bluetooth chips should do in order to mitigate this attack, or at least like reduce the consequences of these attacks. The thing is that such mitigations are a little bit problematic in the sense that usually if we consider Bluetooth as a whole ecosystem, like whole system, we try to fix some part of Bluetooth, like maybe we fix one attack or the other one, but it's still vulnerable like in a whole. So these patches are not ideal, but also if we look in how to fix Bluetooth protocol stack, we also need to acknowledge that we need some universal fix, like a unicorn that will just fix everything on the whole protocol stack and against all the attacks. Because if we just patch everything, this is gonna be not so nice. Maybe we even introduce some more vulnerabilities. The other problem is that we want to have it backward compatible. There are pacemakers, for example, that use Bluetooth, and of course you do not want to make a surgery in order to change the hardware or anything. Or maybe less dramatic example is we do not want to get a new phone each time there is something changed in the protocol stack on the really low level, the physical layer or network layer. So it means that we cannot change the protocol itself when we think about the mitigations for these attacks. And it also a little bit limits us that the devices do not store the transcript that they exchange. So when we run this initial connection, the devices only remember the address of the device, of the partner, or the keys, maybe some other keys that were derived, and that's it. So we do not store all the information that was exchanged, sometimes not even the input and output capabilities or other capabilities. And this also makes the fix very challenging. So before I present the fix, we need to think about what is wrong with the pairing procedure from the cryptographic point of view. So if you remember the picture that I showed with the distribution of the attacks, they were mostly on the initial connections. There was some also for the reconnections, but it was mostly like against legacy. So what we did in the AsiaCrypt paper, we analyzed Bluetooth protocol as trust on first use model, and this means that we allowed the adversary to be passively secure, to be passive in the initial connection, so the adversary can still eavesdrop the communication, can connect with some other devices, but we do not even aim to protect these devices. But during the reconnections, when the devices already established the long-term key and the link key, the adversary can do whatever. It can drop the messages, can modify them, reveal some session keys, and this way we could achieve the security for Bluetooth, the probable security. Questions so far here? All right. So now the natural question is, okay, how can we do a little bit better than trust on first use, so that how we can make Bluetooth secure also against active attacks during the initial connection? So one natural candidate is, okay, we can just use out-of-band communication. We can use, I don't know, QR codes or NFC and so on. The problem with this solution is that it requires some physical capabilities from the devices. For example, in order to exchange the N3C messages, you need to have the N3C receiver and the sender. And this is not the case for all the devices. Another possibility to fix this is what Signal and WhatsApp, for example, are doing. So the user will be shown with some maybe QR code to scan or some digits to compare and verify. And this way, we can have also reassurance that, okay, the key that is derived is secure, or it was derived during the honest execution. Again, the problem here is that you need to have a screen to show such things. And also not all the devices, for example, support the QR code again. Another opportunity is to use the pre-shared key, for example, in TLS research mode. But the problem is that we still need to somehow distribute this pre-shared key. And in TLS, for example, what they do, they first establish the connection in the regular execution, and only then they can use PSK to authenticate further. So this would correspond exactly to the setting of TOEFL that we analyzed in the AsiaCrypt paper. All right, so what we did in CCS paper is we thought, okay, we can actually run another protocol just like on top of Bluetooth on the application layer. So if you think about Bluetooth, it takes all the layers from the physical layer to, I don't know, the association or presentation layer, and then it has application on top, and applications are up to the designers or developers to make. So we can make such an authentication step on the application layer. This is good because we can try to link the derived long-term keys to the authentication, or link authentication to the derived keys that we had. I see another question.
Yes, I'm just curious. So when you talked about this QR code scanning kind of fixes, is it somewhat similar to when you did the confirmation in your high-level protocol? If you move that confirmation to the end of the protocol, is it somewhat similar? Would that help in any way?
Yeah, so the key confirmation, I guess you're talking about in the initial connection. The problem is that it's still, it's exchanged during the connection within the Bluetooth band. And because we want to protect exactly the Bluetooth channel, we cannot let the adversary to modify this key confirmation. And here you can see that it's out of band, right? We have the user who is entering the digits or comparing the digits,
Yeah.
checking the QR code.
But isn't the key confirmation not maybe exactly what you're calling key confirmation, but there is a human authentication step involved, and I'm wondering if you move that step in the Bluetooth authentication protocol to be the last step, would that help? Because I think the way you explained, as I understood, is that process happens after that. There are some key exchanges that are happening. So instead, if you could move, say, the PIN confirmation to the end of that step, is it somewhat similar to doing an out-of-band QR code scanning? Would that help?
This is actually a really good question, because I was also thinking about this. Because in passkey entry, for example, what you do, you enter the digits first, and then you exchange the nonce and so on. So it's possible to even brute force it in the future. I was also asking this question myself, but then we again have the same problem that not all the devices have this input and output capabilities. So you will again have the problems that it might be downgraded. So as a temporal fix, I think it can be true, but you're saying that if you just, for example, move passkey entry to the later point, or if, I'm actually not sure if it's possible, but I think we can also do the key confirmation because it happens at the end of the protocol. We might try to make it also out of band, but here I'm not sure how Bluetooth protocol stack interacts with the application. Like, is it possible to show to the user this confirmation MAC as some, I don't know, user-friendly string or QR code or, I don't know, emoji, whatever? I don't know if it's possible or not, but it could be a solution, yeah.
Thanks.
Yeah. All right, so coming back to the authentication step, where we try to link the authentication to the keys that we derived during the initial connection. So the good part about our solution is that it does not introduce any new functions. So whatever is there in Bluetooth core specification already, we just use it. Another good thing is that it can run at any point of time. So you can, for example, pair, then you can reconnect again, and at some point you can run this authentication. This is also good for low energy devices because it might happen that you did the initial pairing, for example, and then you run out of battery and then you disconnect it. So you do not want to lose this connection when you reconnect, and then you can do the authentication. So you can just postpone and defer this outside the first use. So our solutions are based on the challenge response scheme, which is not some rocket science, but it works. And we propose two types of the schemes. So one is based on the Diffie-Hellman, and one is based on the signature. So why does it exactly work? So if we think about initial connection, when we go into the trust in the first use model, then it means that whenever the execution was honest, then all the consequential, like all the following reconnections, they will be also secure, like TOFA secure. And if we run the initial connection again, if we pair again, and it was a genuine connection again, then we can get the same guarantees that, okay, it was also the reconnection will be secure and the following reconnection. But now with what we call DOFU, so defer outside the first use, whenever we run authentication, we also make sure that the previous connections were secure up to the initial connection. And if we run the authentication in the lower part of the screen, then we will again guarantee that not only the following connections, but also up to the initial connection was secure. So there was no adversary who did something. Right, so here I have the signature-based authentication, and it might get a little bit more technical, but I hope you will bear with me. Are there any points by now, or questions, or comments? Okay. So we again look into the setting of two devices. They already derived. Okay, here I look at the classical version, so I call the keys as link keys. But for signatures, we also need to have some pair of the secret and public key, and also the certificate. So what we have, we ask the devices to generate some challenge, which will be 128 bits long. Then the initiator sends each part of the challenge, and the responder will compute the authentication data, which consists of the challenge of both parties and computed over the HMAC using the link key that they derived during the initial connection. Then the responder will sign this data using the secret key and send everything together. So send the challenge that it produced, it generated, then also the signature, also the certificate, and the public key. What the other party does, it also computes the authentication data, because now it has both challenges, and it also verifies the certificate that it received and checks the signature if it's valid or not. So this solution is, it looks pretty simple, but it works for Bluetooth, and we actually managed to show that, yeah, for Bluetooth Classic it works, and you can mitigate some of the attacks. So before I go to the attacks, are there questions on the scheme? All right. So you might remember this distribution of the attacks slide from before. So what we could mitigate some of the attacks, like method confusion attack and so on the downgrade of the protocol. And we also could mitigate the consequences of the attacks on exact protocols. So you can see here, for example, we could not do anything against legacy because it's not secure against passive adversaries. So even if we have authentication, the adversary will know the key, so there is no point in this authentication actually. We could not do anything with cross-transfer key derivation because it uses ISCMAC, and this one is not collision resistant, so we couldn't show a proof there. But if it's replaced with HMAC, we believe that it should work. Then we could not do anything with legacy, the attacks on the legacy in reconnections for the same reasons. Yeah, you just cannot do anything with them. But an interesting, from my perspective, is the key negotiation attack. So when we could reduce the size of the key. In Bluetooth Classic, this communication happens during the reconnection and it's not authenticated. So the devices first agree on this size and then they derive the encryption key of this size, and that's it. So we could not use our protocol to mitigate this attack. Potentially, we could use this in Bluetooth Low Energy because the negotiation of the key size happens during the logical level communication. But the problem is that we couldn't show that Bluetooth Low Energy is actually secure in our model for the same reason as the cross-transfer key derivation mechanism is not secure because it uses ISCMAC, and this is not a collision-resistant function. So we couldn't get away from this. Okay, here I have some results. So we compared to two papers that tried to mitigate some of the attacks. As you can see, we do not abstract all the attacks, only some of them. But yeah, you can see the pattern that it's again legacy or the reconnection, so the negotiation mechanism or the cross-transfer. So now I have contribution. Are there any questions maybe so far? Otherwise, I will go to contribution. Okay. So what we did, we proposed this cryptographic method and not user-based to abstract some of the attacks. We proposed 4 options, so 2 for each Bluetooth Classic and 2 for Bluetooth Low Energy. We extended the model that we had before, the TOFO model, and now it also contains the deferrable outside first use authentication. We managed to show that Bluetooth Classic is secure in this new model, but we failed with Bluetooth Low Energy. So this actually concludes my presentation because I really tried to make it high level. But if you have some more questions left, I will be happy to answer them. I think we still have some time. And let me just end on the contribution slide.
Well, thank you, Olga.
Thank you.
Very interesting, actually. there were already plenty of good questions. I see some more.
Really good
Paul?
questions, yeah.
Paul, please go ahead.
So you say you failed to prove BLE is, but you still think it will work? It's just you have not yet completed the proof. What's your, say a few more is there?
So the problem is that we couldn't show that the long-term keys in Bluetooth Low Energy, they achieve key secrecy with our authentication. And the reason is that the long-term keys are derived using ISCMAC algorithm and not HMAC. And ISCMAC is not collision resistant. So it might happen that two completely independent executions, they derive the same long-term key, and the adversary can run the protocol between these two executions, the authentication protocol, and they will authenticate each other because the key is the same, but they were not partnered before. So from cryptographic point of view, they will have different transcript. So they should not be partnered, but it works as an attack. So it could be proved also secure if we use HMAC, for example, but there is no this option in Bluetooth Low Energy. So they only have ISCMAC and they have IS, and that's it. So they do not have any other algorithms.
So does this mean you're worried that your technique will not mitigate these things, or you're not worried but you just can't prove it?
Worried is an interesting word. So we can prove this only if another algorithm is used. Let's put it this way. So we are most certainly sure that the proof will work if just another algorithm will be used, which is collision resistant, not necessarily HMAC, but just some other algorithm that is collision resistant. Maybe it's even ISCMAC, but just like some version of CMAC that is collision secure. I think there are some modifications, but yeah.
Thank you.
I hope this answers.
How broken is this Mac that they use? So I have one more question. So do you know if there's an attack that used this collision? Did it translate to a real attack or not?
Yeah, I actually do not have a backup slide for this, but yeah, it was an attack. Unfortunately, I do not remember the authors, but let me check. Maybe I can do some check here because I had the slide with the attacks. So it was already. Okay, so there were actually two attacks that exploited this. One was on mesh protocol that I said I will not be talking today, and another was on Bluetooth Low Energy. And here on this slide, you can see like the last malleable commitment in Bluetooth. So the idea is the following, that you commit. So also the commitment is computed using this ISCMAC. So two devices commit the commitment, they exchange the commitments that were computed using the ISCMAC, and the adversary can find such a node that fits exactly this ISCMAC. So in this sense, I think it's not one-way secure, if I'm not mistaken how it's called. And the adversary might exploit this by making the device accept, even though it was used with another nonce. I'm not sure if I can explain it well with my hands because I don't have a slide. So it will be two independent executions again. In one, the device will commit. The adversary will try to find such a node that will open to such that will fit the same commit, so that the node that opens on the other side, it really fits this.
So you think the adversary can insert something in the middle, basically? So
yeah, exactly.
Right? Yeah. Okay. Thanks.
Can you hear me?
I can.
Yay, cool.
I'm not sure about others.
Okay, cool. I just maybe one question about the modeling. Like, how did you have to come up with new definitions for these things? Are there existing definitions? Like, and how much of it did you model? Like, do you model all the stages or just one more?
So now I'm really sad that I didn't include more technical part because people are actually asking about this. So let me maybe open this slide. So from this slide, you can see what definitions we had, and they're pretty, I would say, used in the literature. So for example, match security is ensuring that we have the same, I'm not sure how technical I can go, but it can ensure that if the parties have the same session identifier or the same transcript, then they will also derive the same key, the session key. And that there do not exist more than 3 such sessions that have the same session identifier. This is, for example, the match security. Key secrecy would be that the adversary cannot distinguish between a real key that is given in a test oracle and some just random string, that is given. Authentication is just, okay, we agree on each other's identity. It's also pretty straightforward. We had leakage resistance, and I think we also changed the name for a bit so that it does not sound like side channel attack. So with this definition, what we wanted to have is that if we run this authentication protocol that uses link key or long-term key, we do not reveal any information about this key. So even if adversary, eavesdrops this conversation, it will not learn anything about the key. So yeah, these are the notions. So I would say 3 of them are pretty much used in the literature, and 1, at least we didn't find this. But in case you know this one, you can also point to me.
So these are like standard key exchange definitions? Does it match up with that? So you don't have to do anything different because it has this out of band.
Exactly.
Because you do sort of have some kind of out of band human, or comparing the digits or something like that in the middle there somewhere, right? Or does that not? Do you not have to capture that part?
Yeah, we do not capture this. There were some models that tried to capture this. For example, from Chunkosa and Hale, they tried to model the interaction between the devices and the user, but no, we do not do this. We just do not take, unfortunately, the user into account.
So do you not need to? Does that not? Because it seems like that's sort of something you need as part of the protocol. How do you somehow start after that step, or how does that work?
So we just assume that the information that is exchanged through the user is just exchanged out of band. Mm-hmm. So if we have the passkey, for example, that the user reads on one screen and tries to input on the other screen, we just say we inherit this from some out of band channel. I see. Mm-hmm. And this channel is secure, and the adversary cannot even eavesdrop on this.
Mm-hmm. Thanks.
So yeah. I'm not sure if there are any more questions.
Yeah. No more questions? Okay. Well, let's thank Olga again. Very nice, very interesting talk, and
Thank you.
Look forward to we can discuss more of these technical details in our follow-up discussion, which I'll set up.
Oh, definitely. Then it would be with different slides in case I need to prepare some.
Oh,
so that we can really discuss the modeling.
Sounds good. All right. Thank you, everyone. Thanks for joining. Thanks, Olga.
Thank you. Bye-bye.
Thanks.